In this lesson, we will look more in depth at what values to set for different hyperparameters and begin automating our work. Previously, you learned that some hyperparameters are likely better to start your training with than others. What we didn't discuss was what values you should try. This will be specific to the algorithm and to the hyperparameter itself. But there does exist best practice around this. Let's walk through some top tips for deciding ranges of values to try for different hyperparameters. It is firstly important to know what values not to set, as they may conflict. You will see in the Scikit Learn documentation for the Logistic Regression Algorithm that some values of the hyperparameter penalty conflict with some values of the hyperparameter solver. Another example from the ElasticNet algorithm demonstrates a softer conflict that will not result in an error, but may result in a model construction we had not anticipated. Safe to say, close inspection of the Scikit Learn documentation is important. There are also values for different hyperparameters that may be valid, but are very unlikely to yield good results. Some examples of this are having a random forest algorithm with a very low number of trees. Would you consider it a forest if it had only 2 trees? How about 5 or 10? Still probably not. But at 300, 500, 1,000 or more, that is definitely getting there. Having only one neighbor in a k-nearest neighbor algorithm. This algorithm averages votes of neighbors to your sample. Safe to say, averaging the vote of one person doesn't sound robust. Finally, incrementing some hyperparameters by a small amount is unlikely to greatly improve the model. One more tree in a forest, for example, isn't likely to have a large impact. Researching and documenting sensible values for different hyperparameters and algorithms will be a very useful activity. In the previous exercise, you built several different models to test a single hyperparameter, like so. This was quite an inefficient way of writing code. I think we can do better to test the different values for the number of neighbors hyperparameter. One thing we could try is using a for loop. We create a list of values to test, then loop through the list, creating an estimator, fitting and predicting each time. We append the accuracy to a list of accuracy scores to analyze later. This method easily allows us to test more values than our previous work. We can store the results in a data frame to view the effect of this hyperparameter on the accuracy of the model. It appears that adding any more neighbors doesn't help beyond 20. A common tool that is used to assist with analyzing the impact of a singular hyperparameter on an end result is called a learning curve. Firstly, let's create a list of many more values to test using Python's range function. The rest of the code is the same as before. Since we tested so many values, we will use a graph rather than a table to analyze the results. We plot the accuracy score on the y-axis and our hyperparameter value on our x-axis. We can see our suspicions confirmed, that accuracy does not increase at all beyond where we tested before. One thing to be aware of is that Python's range function does not work for decimal steps, which is important for hyperparameters that work on that scale. A handy trick uses NumPy's linspace function that will create a number of values evenly spread between a start and end value that you specify. Here's a quick example that you can see. 5 values evenly spaced between 1 and 2 inclusive. Let's practice trying different hyperparameters and plotting